Okay, we should be live, hopefully, fingers crossed. Good. All right, year 10s and some year 11s maybe. Well done for getting on this live stream. Today we're going to look at nuclear equations. And the way it's going to run is we'll do our usual quick quiz, which sort of recaps the stuff that we've done in the previous 3 live streams. Then I did promise that we would look at the answers for the questions that I sent you last lesson. So I've put the answers onto the document, and so I'll put the document up and we can just quickly check through those. If you've not got that worksheet to hand, don't worry, because obviously the answers will be on the recording, and you'll be able to, once you've got hold of that document, you'll be able to rewatch it back and just check that. But it is worth self-assessing your work. You know, like how we use green pens in class, it's worth going back and finding the work that you did last week, on last Thursday, and going through it and marking it. Okay, so we'll do the quick quiz. I'll give you the answers to last week's worksheet. Then we'll do a bit of teaching about these nuclear equations. Nothing to worry about, but they are quite an important part of this topic, so we need to try and switch on there. And then obviously there's some tasks for you to do on the document. So I'm hoping lots of you have either got this, managed to get this printed out, or you've got it in a live Word document that you can edit, etc. Or if you haven't been able to manage to do any of that, don't worry, you can just make notes and write stuff down. Okay, so we'll do those at the back end of the lesson. Okay, right. So here we go. Quick quiz. Once we've done the 8 questions, I'll switch on the live chat. I've got my moderators in again. Thank you, Kobe. Thank you, Matthew. And yeah, we can see who's here, and we can see how you're getting on this. How you're getting on with the quick quiz out of 8. All right, so let's have a look. Where's the PowerPoint? Right, okay. So yeah, nuclear equations, quick quiz. Let's go. This picture here is of 3 versions of hydrogen: protium, deuterium, tritium. Okay. And this is to do with some of the first questions. So, question 1. What particles orbit the nucleus of an atom in different shells? So, on the diagram that I've got for you there, they're marked as the little blue E's. So, what are those called? Okay, question 1. Right. Question 2. What is an isotope? Okay, we did this in lesson 1 a few weeks back now. Can you remember what an isotope is? There's 3 versions of hydrogen there that are a bit of a clue to that one. Okay, so they're all hydrogen and they're different versions. Can you use that as a bit of a hint and a clue to answer the question what an isotope is? All right, good. Question 3, we'll have to rack our brains here. Can you describe the plum pudding model of the atom? So when we were looking at experiments that have led to our understanding changing of the structure of an atom, we talked about the plum pudding model. Okay, so this model was the first one that wasn't just tiny little snooker ball sort of things. This is the first one that suggested some structure. So can you remember what the plum pudding model was like? Okay, don't worry if not, but hopefully the word plum pudding at least is ringing some bells. Okay, so have a go at that. Question 4. Why was Rutherford's alpha scattering experiment so important? Why was it so important that Rutherford did his experiment? What did he find out? So what was so important about Rutherford's alpha scattering experiment? There's your first four questions. Good. And I've got you on the right screen, which is a bonus. Right, next 4. Okay, this is about what last lesson. All right, so we're starting to understand radioactivity, radioactive decay, and here's some questions on that to see what we picked up. Question 5. What part of an atom can be unstable and give off radiation? It's important you know where the radiation comes from. So which part of an atom can be unstable and give off radiation? Question 6. What is a beta particle? We looked at alpha, beta and gamma and what they were. Can you remember what a beta particle was? Fingers crossed. Question 7. What material is needed to stop gamma radiation? So this this nuclear radiation, okay, some can travel further and penetrate through more things than others. So, which was the one? What material did you need to stop gamma radiation? Because gamma can fly through air and various things, but what do you need to stop it? And question 8: which is the most ionizing form of radiation out of alpha, beta, and gamma? Which is the most ionizing? So remember, that's the ability of the radiation to knock electrons off atoms. All right, which one's got the best ability for knocking electrons off atoms? Alpha, beta, or gamma? There are your 8 questions. Okay. Right. I'll get the answers done. I'll switch on the live chat and we can see who's in and how many we've got out of 8. All right, so let's go. Question 1. Those are called electrons. Okay, we've got protons and neutrons in the nucleus. We've got electrons orbiting around the outside. Okay, so electrons are the particles that orbit around the nucleus of an atom. Isotopes, hopefully you put, it's a different version of the same atom. So it's got the same number of protons. So like in the picture on your screen, there's 1 proton in a hydrogen atom. Each of those 3 versions of hydrogen have got 1 proton. And it's that proton, 1 proton, that makes it hydrogen. If you have 2 protons, it's something else, it's helium. So an isotope, it's an atom that's got the same number of protons but different number of neutrons. You can have different number of neutrons, okay, and still be hydrogen as long as you've only got that 1 proton. Good. Now, plum pudding. The plum pudding was after J.J. Thomson discovered the electron. And if you can remember, he said that you had a positive sphere of charge with lots of little negative electrons embedded in it. Okay, so it was like, that's why they call it plum pudding, because it's like a pudding with plums in it. This is like a positive ball of charge with electrons in it. All right, so that's what plum pudding is. And why was Rutherford's experiment so important? Because it led to the discovery of the nucleus. So if you look at our pictures again of the hydrogens, though the nucleus, that central part, the protons and neutrons, that's what the alpha scattering experiment found out. It found out that atoms are mainly empty space, but they've got this small nucleus that's very massive, because they were getting alpha particles rebounding the way that they'd come from. So there must be something in there. They discovered the nucleus. That's why Rutherford's experiment is so important. Good. Right. Next 4. What part of the atom can be unstable and get off radiation? That's the nucleus. When we're talking about radioactivity, we're talking about stuff that's being given off from the nucleus. Okay? It's really important you remember that. Some atoms have got a stable nucleus. They just sit there doing whatever they're doing their chemistry or whatnot. Some atoms are unstable, and they need to become stable by giving off alpha, beta, or gamma, essentially. All right? What's a beta particle? It's an electron. Tricky, that, isn't it? Because electrons are normally the particles going around the outside, and these electrons are coming from the nucleus. Okay, there's some stuff that goes on in there that means the nucleus sends out an electron. So it is an electron, but it's coming from the nucleus, a beta particle. Gamma is stopped by lead. And the most ionizing form of radiation is alpha. Okay, so alpha particles can knock electrons off atoms better and more effectively than beta particles, electrons, or gamma, which is an electromagnetic wave. Okay, so there are the answers to your quiz. Before I show you the answers from last lesson, what I'll do is I'll get on the, I'll enable a live chat, and then you can tell me what scores you got out of 8. So just bear with me while I do that. Okay, so I think you're still looking at my webcam, but I've enabled live chat. So if you just post in there, post your scores. Let's see how we're getting on. All right. And I've put slow mode on. I'm not actually entirely sure what slow mode is, but there we go. Yes, brilliant. Well done, full marks. Excellent. Lydia, superb. Who else is there? What else? How else are we going on? I don't know. Brilliant. Excellent. Well done, Kira. Well done, Kobe. So we're getting this stuff, or we're remembering this stuff from when we've done it in previous weeks. So, yeah, very well done, folks. Good. Right. If I bring us back here, we should be looking at the PowerPoint. What I'm going to do, I'm just going to, because I promised this, I'm just going to run through the answers from last week's worksheet. So you should, I'm hoping, be able to see those now. I'll check that. Yeah, you can. Good. Right. So I'll do this quickly because you can always use, and because I want to get onto the new stuff that we're doing today, but you can always use, you can always watch it once it's been uploaded and pause it, etc. if this is going too quick. So don't worry if you haven't got the document there, but I'll just run through this and then it's there for you to go back to. All right, so we'll do this quickly. So beta is an electron, alpha, 2 protons and 2 neutrons, gamma, electromagnetic radiation. All my answers I've put in red, obviously. So gamma, you can see it going through the paper and aluminium but being stopped by the lead. Beta will get through paper stopped by aluminium. Alpha won't even get through our skin or through paper. Okay. Correct answer, particles in the nucleus of the atom are the neutrons and the protons. Electrons are in the shells, remember. All right. And the charges, the neutron is neutral, so 0 charge, protons +1. Right. An atom is neutral because you have the same number of positive protons and negative electrons. So let's say you've got a helium atom and it's got 2 positive protons, so it's +2 charge. You've got 2 negative electrons, -2 charge. So the +2 and the -2 cancel out, therefore it is neutral. Okay, so same number of positive protons as negative electrons. Atoms that lose electrons are called ions. That's why it's ionization. And overall, if you lose a negative electron, you've got 1 more proton now than electrons because you've lost an electron, so you're overall positive. Okay. Gamma is the least ionizing. It is ionizing, but it's the least ionizing. And like we said before, if atoms are ionized, they lose an electron from its outer shell. They can gain electrons to become ions, but when we're talking about radioactivity, it's about them losing electrons, them being knocked off by alpha, beta, or gamma. Okay, right, in this diagram, we've got a electric field between 2 plates, a minus plate and a positive plate. The alpha particle, it's a positive particle, isn't it? 2 protons, 2 neutrons, so it'll be attracted to the negative, so P is the correct line as it deflects upwards. And the other way around, gamma, the one going straight through the middle, not affected, mustn't have any charge, which is gamma. And then obviously the electron, the beta decay is R, because that's a minus electron being attracted towards the plus P. So P for the alpha, Q for the gamma. And you want your gamma in a lead box because that'll stop it. It's the only thing that'll stop it out of those 3. Alpha in the cardboard's fine, and beta the aluminium block. So those are the answers to last week's worksheet. I'm not going to dwell on them because I want us to get on with the learning for today, but they're there for you. You can peer assess that, or self-assess that. Do it in green pen, same as you would at school, in your own time. Right, back to what we're doing today. I'll just check. The hardest thing about doing these lessons is I get no feedback as to what you're looking at. I have to check my encoder or trust that I'm pressing the right hotkeys, which I don't trust. But you are looking at the PowerPoint. Come on, Mr. Barnes. Confidence in your own pressing of buttons. Now, all we're trying to learn, okay? On my watch, it's 2:15, so we've had 15 minutes of this. We might get away with 40 minutes here because there's just one learning objective for today's lesson. Remember, next week's half term, there won't be any live stream lessons. Use it as time to catch up if you need be on the ones that we've done so far. Okay, you've had all the documents as emails and on your Sims app, so just take your time to come back and get up to date, because they'll start again after half term. So we are trying to understand how to use nuclear equations to describe alpha, beta, and gamma radiation. So I'm going to explain it. You're going to do a task. We'll go through the answers today. Won't take a sec. Jobs are good. So let's start with alpha. How do we describe alpha decay with an equation? So here we've got a nucleus, and it's obviously unstable because it's giving out radiation to try and become stable, and it's spat out an alpha particle. Now that's 2 protons and 2 neutrons. This is why I've put the helium-42 next to it, because that says there's 4 particles altogether in an alpha, 2 protons, 2 neutrons, and the 2 tells you how many protons there are. It's a bit like, well, it's very like the information that's represented on the periodic table, where you get the atomic number and you get the mass number. Okay, so let's say this, in my example, this unstable nucleus is radon 86. So that's radon 21986. Okay, and obviously, so we've got 219 particles in the nucleus altogether. 86 of those are protons. Okay, and it gives out an alpha particle to try and become stable. So it's lost 4 particles altogether from its nucleus, 2 of which are protons. So hopefully you can see that what happens is your atomic number, the bottom number that started as 86, you've got to take 2 off it because it's got rid of 2 protons. So it goes down to 84. And then the top number, the mass number, that goes down by 4, okay? Because you've got rid of 2 neutrons and 2 protons. So 219 drops to 215, goes down by 4. And the number of protons goes down by 2. So you end up going from radon to polonium. And it's a different element now, isn't it? Because as soon as it's got a different number of protons, not got 86 anymore, it's got 84, it becomes a different atom. And you can look it up on the periodic table and see what it is. So that's what happens with alpha decay. That's the equation for alpha decay for radon turned to polonium. Now, in general, and don't worry about this, the thing to remember is alpha decay takes the top number down by 4 and the bottom number down by 2. That'll get you the marks in the exam, okay? The expression there I've put in for completeness is just showing you it doesn't matter. This is the same with whatever element you've got. You take 4 off the mass number and you take 2 off the atomic number, because the protons have dropped by 2 and the number of particles in the nucleus have dropped by 4. So that's an alpha decay equation. You've got all this information in the knowledge organizer on the sheet that I've given you, so don't worry about having to try and write it down if you've got the sheet. Okay, what about beta? Beta is an electron. Okay, so here this time, we won't have radon this time. Here we've got carbon. Let's say we've got carbon. Carbon 14. So we've got 14 particles in the nucleus, 6 of which are protons. Okay, and we give out an electron this time. Now, an electron doesn't change. When it gives out an electron, it doesn't change the total number of particles in the nucleus. So the total number stays at 14. But what happens, where this electron sort of comes from, is a neutron in the nucleus turns into a proton. It's clever stuff. We don't need to know the details. And you get an antineutrino to conserve electron number. And there's all sorts of brilliant stuff that if you're interested in, you should do A-level physics, because it's amazing, the standard particle model. But we just need to know that when you do beta decay and you kick out an electron, your top number stays the same because you've got the same number of protons and neutrons in there, but your atomic number just goes up by 1. Basically, you turn one of your neutrons into a proton and get rid of an electron. That's how it works. Okay, so carbon here, 14 stays the same, but the proton number goes up by 1 because you've changed a neutron into a proton. basically. An up quark is actually, no, a down quark has changed into an up quark. And again, if you want to know about quarks and stuff, A-level physics is absolutely the way forward. Good. Now, there's the generic thing. It's just saying the top number stays the same. The bottom number, the proton number, you add 1. Because you're adding 1 and the protons are changing, you've got a different element. It's no longer carbon because you've now got 7 protons in the nucleus, so it's nitrogen. Okay. Gamma is the easiest one because nothing happens. It's an electromagnetic wave, remember? So it's just radiating energy away from the nucleus. The nucleus wants to become more stable. It needs to get rid of some energy. So the energy, because we have conservation of energy, you can't just get rid of it. It has to be transferred something, or it's transferred by the gamma wave. So if we've got barium, 137, and it gives out a gamma, nothing changes. It stays identical because no particles have been emitted, or no particles in the nucleus have changed from a neutron to a proton, etc. It just stays the same, and we get the energy carried away as a gamma. Okay, so there it is, just stays the same. Right, brilliant. Hopefully that stuff makes sense. I think it's quite logical if you just take the time to think, what is an alpha particle? Oh yeah, it's 2 protons, 2 neutrons. So we know that the top number's going to go down by 4, the bottom number by 2. Beta is the harder one to remember. I just remember top number stays the same, bottom number add 1, change the element. Okay, and gamma, nothing happens. Okay, right. Your turn. There's some exam practice questions. I think there's 8. I can't remember entirely, that are getting you to complete these equations. Okay, so if we look here, for example, the first one with bismuth, I think Bi is in tellurium. We're getting to the limits of my remembrance of not so common elements. Tellurium, I would imagine. What you've got to do is you've got to fill in the squared boxes. So you've got to say, okay, there's bismuth. It's giving out the alpha particle. What's the top number going to be now? What's the bottom number going to be? Next one down will be beta, and so on. So I want you now to have a go at filling in your sheet. I'm going to go into the chat to just check that for any questions about this stuff. All right, so if you've got questions or you're struggling, go to live chat. I'll keep an eye on that. I'll also look at putting some answers into the document, because I've got the document here. So hopefully now you're looking at the sheet. And I'll go through and I'll put some answers in so we can quickly recap the answers at the end. Right. Also, let me know in live chat when you've finished. All right. I think I'll leave the document up for anyone who hasn't had a chance to print it off, and I'll get the I'll get back. Keep me on the chat. Right, so there you go. There's the first 4. If you didn't have a chance to get the sheet printed, just jot them. If you've not got a sheet, just jot them down. See how you get on with them. So no, yep, good. Kira, don't worry about losing the sheet. Finian, brilliant. Kate, well done. Hello, Taylor. Good to see you're in again. Brilliant. This. If you've lost your sheet, there's no dramas. The way to do that is jot them down off the screen, because I've put them on now, Kira. In a few minutes, I will scroll down to the second 4, the second lot of 4, and then you can either, if you can't find your sheet or if you deleted it, you've got them recorded on the live stream, haven't you? Otherwise, you can just reopen your sheet at a later date and come back and check the answers. Half-life, Lydia, is what we are doing in our next live stream. If I don't, hang on. So what I work, if I've got your spec here, look, and I just make sure we're covering everything that you need to know. And I've put down in here what the lessons are going to be. Yes. So Lydia, you're right. Oh, right. So Kira, don't worry about the one that you've from last week. You've got it on email if worst comes to the worst. And if you deleted it, email me and I'll send you a new one. So no stress at all. Lydia, Half-Life is next, not next week, 'cause we're on half term, but the week after. Jess, right, I'm going to scroll these questions down and then I'll come back to your question, Jess, about Decay. So that should give you... Oh, check that. Yeah, I can see them now. Right, I've scrolled them up. Right, Jess, good to see you for a start. Glad you're on this. Decay is where an unstable nucleus emits alpha, beta, or gamma to become stable because it changes. The nucleus decays. It loses energy via the emission of alpha, beta, or gamma. So radioactive decay, so nuclear radiation is alpha, beta, and gamma, and neutrons, but don't worry about them. They don't ask you about them. Okay. So nuclear radiation is the alpha, beta, and gamma. So, oh, there's an alpha particle. What's that? It's not decay. It's nuclear radiation. Okay, the stuff that they worry about when they're doing nuclear power stations, etc., etc. Radioactive decay is where the nucleus breaks down to become more stable by emitting an alpha, beta, or gamma. Hopefully that answers that question. Okay. Give me a heads up when you are... Hi, Matthew. For fear of antagonising people, great team you support, mate. Well done. Yeah. Give me a shout or give me some indication of how you're getting on with these, because obviously we're halfway. We've done half an hour now, and then what we'll do is we'll go through these answers. Okay. Any more questions? Keep sticking them onto the live chat because I've still got that. I've still looked at that. How are we getting on? Let me know how we're getting on. Oh, that's because that's on. Right. I should have turned slow motion off between settings because I've worked out now that it's trying to block it for 60 seconds, innit? I wondered what slow motion in the chat was. It should now. It still says slow mo's on. Should have turned it off. Sorry about that, folks. My mistake. I didn't realise that slow motion on the chat means that it doesn't let you put something else on for 60 for a minute. So obviously that's a setting that I need to keep off. Although I think it doesn't look like it's letting me change it midstream. Okay, I think we're having some issues with our chat here because I'm getting a message now saying that I'm unable to connect to chat. My mistake with this slow mode, I didn't realise that limited it to one response per 60 seconds. I've tried to change that and it might have sent it into a bit of a spin. So what I'm going to do, to finish off, I'm going to go through the answers to these nuclear equations and then we're going to call that a day. Yeah, apologies about the chat issue, but from now on, obviously, I won't enable the slow mode when I set the stream up. Right, okay, let's have a look at these, and then we're done, which is good. Right. So you should be able to see my sheet now. I'm going to put these answers in. So, and you just mark them off. Make sure you're getting your head around this properly. So if we start with bismuth and it loses 4 particles, the 1011 has got to drop to 207 and the 83 is going to drop to 81. Okay, it's quite straightforward these if you remember how we do them. Strontium for beta, remember the top number does not change. The relative mass stays the same. It's the atomic number that goes up by 1. So that's to 39. Okay. Gamma. Does anything happen? No. So this stays at 6027. And now, a bit more involved this. I would always put in the relative atomic mass and the atomic number for your alpha particle or your helium nucleus. They put He for an alpha particle because it's the same as a helium nucleus. A helium nucleus is 2 protons, 2 neutrons. That's why you see it in your exam, and they say in the specification that that's how they will represent it, which is why I want you to see it like that. Put that in, and then it's the same process. So the 237 needs to be dropped by 4, so that's going to go 233. And the 93 is going to drop by 2, which is going to drop it to 91. Okay. Same thing. Put the numbers in, 0 minus 1. Okay. And then you can do the same thing. So 131 stays the same, but of course a neutron's changed to a proton. So xenon goes up, iodine, sorry, changes to xenon, goes up to 54. Okay. Now, gamma, nothing happens. So this just remains identical. Okay. Just going to check my code. You are looking at this, otherwise, yeah, good. So here, we have alpha. So let's say 4,2. So this has got to drop down to 2,6. Take 4 off it. And this is going to drop down by 2 to 88. Okay, so that's how they work. Once you get your head around them, they're fine. Alpha, top number down by 4, bottom number down by 2. Beta, top number stays the same, bottom number up by 1. Gamma, exactly the same, it's just energy that's being carried away. Okay, this is harder because I've put that in as an image. This is harder for me to do, but I'll write it here. Right, so let's have a look. We need some additional detail here, don't we? Barium has an atomic number of 56, so that's got to go into the bottom there. And then obviously, it's decaying by beta decay. So the top number stays the same, the bottom number goes up by 1. So it's going to be difficult for me to do this. I'll tell you what, I'll try and do it like this. So we need 57. Because if you've got beta decay, that'll do, you understand what I'm saying there. It goes up by 1, and then of course we would just need our beta particle, which would look like that in there. Okay, so that's what you have for question 8. Question 9, thorium-232 gives out an alpha particle from its nucleus, and it goes on to tell you there how that works. Okay, now thorium-228, okay, also decays by alpha particle, so it's just saying, can you do the same thing for thorium 228? And of course, we're going to get, if it's alpha, I'm just robbing this so it's easier for me. Okay, let's have a look. Now, we'll get this altered up. 228 gives off alpha. That's going to go down by 4. Okay, so we're going to get 224. The bottom number is going to go down by 2, which is 88. Oh. Bear with me. Right, that's better. Now, we know elements, we've talked about isotopes before, elements with the same number of protons are always the same type of atom. So I know from up here, so this part where it says 88 is, it's not radon, is it? The radinium or something like that. Decent guess that. So we know that's Ra because it's 88 and this one's 88, and there we go, we got it done. All right, so let's see. You should now have had chance to look at an explanation of nuclear equations, because that was our objective. How do we represent alpha, beta, gamma with nuclear equations? Do those questions and then look at the answers. Now, of course, with the self-assessment and marking them, you might have to come back to this once it's uploaded, but that's absolutely fine. That's part of the beauty of it. You can access it when you need to. Okay, so today it's been a fairly short live stream. I'm just going to check the chat quickly. Again, I think we've had an issue, but we shall see. Yeah, so unable to connect to chat. So I'm not getting your chat feed through, unfortunately. Please try again later. What I might try, I'm going to turn it off and back on again. That old trick. I won't leave it 10 seconds. I don't believe in that rubbish. But I'll just disable it. Save it. And then try and enable it again. And hopefully you'll just have one last chance to ask any questions about the stuff that you've just done there. So enable live chat. Allow replay. Don't enable slow mode. Right, yes. Good, okay. Right, Taylor, it's difficult. That's why. So, it's about patterns though. Taylor, it's about looking at the examples. Really look at your examples, and also look back at the answers that I've done, and then it might give you once you see the answer to a question, the question becomes obvious and easy. Like, oh yeah, no, I get it now. So that's one thing to do, and the other thing to do is if after you've had a look at it, Taylor, you still don't understand it, send me an email, and I will send you some additional stuff. I can send you like another video done by someone else to watch on this stuff to see if that can help you. Because obviously this is just my explanation, and it's like anything we teach, and you've got to try loads of different ways to get people to understand it. So if you're still struggling, and this goes to anyone out there, okay, just send me an email, and I'll send you some links to some additional study material that will help you get your head around it. All right. Hopefully that's okay. Right. Any more questions before I sign off? You lot as usual been brilliant. It's a lovely sunny day, so well done for getting in and getting this done. Like I said, I won't see you next week. We'll start again. There'll be a fundamentals lesson on Tuesday. I'm going to say the 2nd of June, and then there'll be the lesson about half-life. Brilliant, cheers, Taylor. There'll be a lesson about half-life on the Thursday. So nothing next week. Then your standard 2 lessons, your fundamentals, and your atomic structure specific the week after. Right, okay. I'm going to sign off. Stop the speed. Well done, folks, and have a great half-term holiday. Chill out, take it easy, and we'll get back to this on June the 2nd. Right, bye for now.